Thank you, sir. Thank you. Today, we are going to go to slide 65. Here we go. There was a question that I received yesterday about explanation of the way how the factorial function is working. So this was the factorial function. You see it on the screen? Factorial, visible or not visible?
Yes, Professor, visible.
Yes, okay, thank you. Factorial of n is 1 if n is less than 2. So if n is 0 or n is 1, factorial should be 1. If this is not the case, then factorial of n is f if I can compute n minus 1 and then compute the factorial of n minus 1 and then multiply this factorial by n to get f, which is the result that is returned here. Now, this has looping. Therefore, when you go to compute factorial, for example, of 5, since n is not, 5 is not less than 2, we are going to fail this line and come to line number 2. So you can never reach any line unless you fail previous line. So you have to fail line number 1 to come to line number 2. So when you go in line number 2, in rule number 2 here, and you activate factorial of n minus 1 to get f1, you again jump to the first line. So from here, you jump to the first line, fail, come to the second line, fail, come to the first, second, and then after that, when you have this satisfied, the first line, when you get this one, then you are returning from this factorial multiple times. Now, the question is that this is not very simple. And if you want to see how this works in detail, what you can do is to instrument this program with right statements so that you can trace that. So the next question is how to instrument. Well, use write command, a new line, nothing particular. So what I have here is program that is instrumented for trace. So instrumented factorial program for trace. If you want to see the anatomy of execution of recursive calls, then what is framed here are original commands. But here I write for each position. For example, when I come here to factorial of n is 1, you write rule 1 entered with argument n equals n, so that you know that you entered this program with this value. And then you compute n equals 2. And if you, n less than 2, and if this is true, then you are going to go to cut. And after cut, you are going to write R1, exit R1 after the cut, returning the result 1. So this is what happens when you enter and when you exit from this rule. So if I come here and say, give me factorial of 0, n, then I'm going to display entered with argument n equals 0 and exit R1 after the cut, returning the result 1. So this is rule 1, after the result 1. And you get the result that comes from a PROLOG, which is 1. Factorial of 0 is 1. However, if I have factorial of 5, then I'm going to enter rule 1 with n equals 5. What's going to happen then? Well, we are going to fail R1 because we don't have that 5 is less than 2. So failed R1, entered rule number 2, and activated factorial with argument 4. After that, we again jump to rule 1, enter with 4, and fail R1. So you enter, fail, enter, fail, enter, fail, enter, fail up to the end. So what I have here is that rule number 2 is instrumented with this write command, failed, because you cannot come to 2 unless you failed R1. So you first fail R1 to come to R2. And then entered with argument n, and then we compute n1, which is n minus 1, and then you say activated factorial with this n1, which is a new value, and to compute f1. Okay, and then you are activating this factorial. So the message will be activated factorial 2 and f1. And then you don't return f1, but you are jumping again to rule 1. So after that, if you succeed and exit from this factorial function, then you can say computed f1, which is f1. So this is what is the message that I put after that. And then if you reach this point, say multiplied n times f1, and then n computed f, which is the result that comes here. So at the end, you have multiplied, when you start coming out of these recursive calls, multiplied 2 times 1 and computed 2. And then multiplied 3 times 2, and then 4 times 6, and then 5 times 24 to get 120. So practically, you are going out of all these recursive calls and creating f1 is 1, and then 2, and 2 times 3 is 6, and 6 times 4 is 24, and 24 times 5 is 120. So you see the anatomy of the execution. And this is good for studying and good for getting insight how this works. So if you have a program that you cannot follow directly and you don't understand how it works, it is always advisable to put a couple of write commands inside. Now, I put here you cannot put more detail that I put here. So, but I still had to put 1, 2, 3, 4, 5, 6, 7, 8 write statements if I want to show each and every detail where the search engine is currently. Go ahead. What's the question?
Sorry, Professor, that was a mistake.
Okay, no problem. So what you can always do in each program that you write, you can put these print statements so that you display where the search engine at that moment is, so that you can have the trace of execution in your own words, in your own homemade trace. There are other things like debug, etc., that language processors have, but this is not available in each and every language processor. So when you want to understand how something works, put your own writes inside to see intermediate results, and then you get trace in full detail. Enter with argument, fail, enter with other argument, fail, enter with this argument, succeeded, and then exit from function, computed this value, multiply 2 times 1, and then when you watch this trace and you see the program itself, therefore this program here, you see exactly how search engine is going here and failing and never reaching cut and dropping down, and then computing n1 is n minus 1, activated factorial with n minus 1, and then going back to the beginning, and then again failing and coming here, going to the beginning, failing, coming here. But as you're coming here, you have that n, which is initially, for example, 5, is going to be 4, 3, 2, and finally 1. And when you come with 1 and jump here, you get as a result 1. Now you have this result 1 that comes out of it, and then you multiply 1 times 2, and then 1 times 2 times 3, and the result times 4 and 5. And at the very end, when you come to the last one, you return here 120. So you are practically looping here and looping through this initial part. So this is clearly visible in this exit, multiply, and finally you get the result. However, of course, after a little bit of practice, you will see that in your mind without writing this, but it is useful if you want to see this working. So I sent these slides to you yesterday in email, and I hope that you received that. And if you have time, put these few write commands inside and play with that to see how it works. Okay. Another thing that you can do is to see a little bit of flexibility in factorial function. So in the case of factorial function, we have two variables, the value that you want to have factorial computed for, like this n, and then the result f. So you can say, I have two variables, n and f. N is the argument, and this is n factorial. So I can give n and ask, give me factorial. Or I can give n and f and ask, is this correct or not? Or I can give factorial and ask, what is n? I can give here factorial 120 and ask, what is n to give this factorial? That would be the full flexibility. Of course, you cannot have full flexibility whenever you have is inside. If you have assignment, assignment is multiplying two numbers. And when you multiply two numbers and get the result, you cannot go back, simply because it is not clear if the number is 120. I cannot say which two numbers produced 120, because it could be 12 times 10 or 24 times 5 or whatever else. So obviously you cannot find, because there is an infinite number of components that can produce the same result. You cannot go back. So this is called flexibility or inflexibility. So in the case of factorial, argument is this 5. So this is input and n is output. And if I ask, give me factorial of 5, PROLOG is answering n is 120. So this is the output and it is correct. Everything is okay. However, you can also ask, is factorial of 5 120? You give both of them as inputs. And this version of PROLOG is capable of answering true. That means it is going to compute factorial of 5. It is going to get 120, compare with this input that we provided, and will say true. Yes, that is true. However, if you say, give me argument n, so that n factorial is 120, this is asking too much. You cannot get this result. And the message that you obtained as error message is arguments are not sufficiently instantiated. Not sufficiently instantiated means that there were some arguments that were strictly inputs, and you were not giving these inputs. We have not given the input. So by the nature of the program, this n is strictly input. It is used to compute n minus 1, again with this assignment. So you have two assignments inside, and you cannot go back to find how this computed, because these are assignments. And therefore, when we come here, PROLOG knows that n is input argument, 120 would be output. However, you cannot go back, and therefore input is not given, and I cannot compute the output. And this is the reason for this. Message arguments are not sufficiently instantiated. For example, if you multiply 3 times 2.5, you get 7.5. You can always find 7.5 if you multiply these two numbers. But if I give you 7.5 and ask, tell me what are two components that produce this 7.5, this is not possible, because there is an infinite number of products that have the result 7.5. So you cannot decide which one is one that was used to compute 7.5. So this is what we have here, more or less the same thing. So we are going to find this error message in all cases where we try to get output without giving complete input. So arguments are not sufficiently instantiated. That means some of inputs is missing, and therefore I cannot compute the output. That's the point. And here are more error messages, but that's it. Then we go now to slide 91. And this was the slide about pattern matching. And the problem was to write the program that is going to show components of a list. So you have here list 1, 2, 3, and we want to show these components 1 and 2 and 3. So the question is how to write the program that will, for this list 1, 2, 3, show element 1 and then element 2 and then element 3. How to write such a program? Well, you can say to show the complete list, I am first going to chop the head, which is this 1, and we'll display this 1. And then after that, we'll ask, show me the tail of this list, which is 2 and 3. And by doing that, sooner or later, I'm going to come to an empty list. So if I have empty list, showing an empty list, we'll just put the new line and nothing else. So this is this new line here. After I finish showing all elements. And how to show the list that is not empty. So for empty list, we put just new line. If the list is not empty, then it has head and tail. Therefore, I am going to display head, put 1 space, which is 1 space here between 1 and 2, and then say, show the list of the tail. So to show the list that has head and tail, show first the head, and then show the tail. And this is giving you 1, 2, 3, all components. When you come to an empty list at the very end, put new line and exit the program. So this is typical tail recursion. We can, of course, use vertical line for pattern matching between lists. So if you say, I have the list 1, 2, 3, 4, 5, and I want to match that with A, B, and here is sublist C. Then A will match the first element 1. B, second, will match the second element 2. And this C is going to match everything that is rest after 1 and 2. So this is 3, 4, 5. Therefore, you are going to get the result A is 1, B is 2, and C is 3, 4, 5. 3, 4, 5. Therefore, that's what is the result here. You can also say, I have list 1, 2, 3, and I want to match this with A, B, C, and D. Of course, after these 3, since this is the proper list, we have an empty list. So A matches 1, B matches 2, C matches 3, and D matches this empty list at the end. So you get 1, 2, 3 in this way. The idea is this, that you have 1, 2, 3, and empty list at the end. So you have these 4 components, 1, 2, 3, empty list. And this is the proper list. So when you go here and you have 1, 2, 3, that is matches to A, B, C, and D, then we have that A is matching 1, B is matching 2, C is matching 3, and D is matching this empty list. So that's how this matches in this case. So 1, 2, 3, and empty list. You can also try to match 1, 2 with A, B, C, D. Well, now you have to instantiate 4 components, and you only have 2 to match. And then there is no match because the length is different and you cannot match that. Answer is no. It should be that way. This here is syntax error. You cannot put 2, 3 here, or you put them in, but you put them in the list. So here is the error in writing. And here is 3 components. First is 1. Then you have pair, 2 and 3. This is not a list. This is just a tree. that has binary 3 that has here 2 and here 3. And then the third element is 4. And this is the correct list. So you have 1 and 2, 3, and 4. You can also have 1 and as a head, and then the tail is 2, 3, 4. Is this matching 1, 2, 3, 4? Yes, it is, of course, because this is the list. So right of the vertical line should be a list. So 1 is a head, 2, 3, 4 is the tail, and this matches 1, 2, 3, 4. Any question? Okay, if I have here 1 and then sublist 2 and 3 and have to match this with 1, A, B, and 3, of course, this sublist is A is 2 and B is empty list because this is this list that matches these 2. And so these elements, these examples are the same. The situation here is practically the same, except that things like this are not the list. So if you have 3, 4, this is not a list. So if I say, is this a list 1, 2, 3, 4, can this match X, Y, Z, T? It is going to say false. But here I have Z and T that are a pair. So Z was matching 3, T was matching 4. But neither this nor that is a list. So if you try to match this with a proper list, you are going to get false, as it should be. Here, when we match XY with first, second, then we have that it gives me false because this here is not the proper list. This here is a pair, and this here is a list. So list is not matching a non-list, a tree. That is not a list. However, if I have XY to match first, second, and empty list, yes, of course, this is the proper list. First is first, Y is second. So X is first, Y is second. This works properly. There is a library function, isList, that tells you whether a construct here is a list. A collection of components is a list if it is terminated with an empty list. So if it is not terminated with an empty list, you get false. If it is terminated with empty list, like here where you have 4 and empty list at the end, then it is true. Okay. And then you can ask, show me this list. So this is equivalent to 1, 2, 3, 4. But if you ask, is this pair a list? No, it is not. 1 terminated with sublist 2, yes, it is. So we have that in the case of binary trees, like this one here, binary tree can be terminated with empty list terminator or can be without terminator. In this case, this is a tree, and this here is a tree that has the properties of list because it is terminated with the empty list. Now, one thing that you have to note here, and I left this in the reader, that after version 7, and currently we are in version 8 of SWI PROLOG, they decided to change the syntax a little bit, and we have to be aware of that. Traditionally, for many years, PROLOG had that binary tree has these nodes that are denoted with dot. So if you have 1, 2, 3, an empty list, this is internally stored inside the interpreter as operator dot, which is this dot here, and then you have 1 and sublist 2, 3, empty list. So practically, this dot has the same role as the predicate likes in likes Yozo wine or likes Iceman wine. Okay, so this is the predicate. Dot is the predicate. However, they decided to use this dot recently for dicts, and to make a dict, the way how this is used is exemplified here. So you have that X matches a point, and then point is something that has two components, X, which is 1, and Y, that is 2. So when you say point is something that has X that has value 1 and Y that has value 2, then you can put this dot here and say, give me the component X. And the component X is 1. And then X is matching this 1 and gives you the result X is 1. So they decided to use dot in the same way dot is used in C or C++ for structs. So this is practically a struct called dict. This dicts can have various components. So you can say box has length, width, and height, and give me width, which is this middle component. And PROLOG will tell you W is 4.56. But they made a sacrifice. They to get this possibility to select to select components from these dicts, they had to use this dot, and dot was no longer available for these constructs. So if you take literature, books on PROLOG, or some other version different from SWI, you are going to find that this is working. And now don't use this dot to make this kind of construct. So you can say X is dot 1, dot 2, dot 3, empty list. This is the way how list is stored in memory internally. And PROLOG should return X is 1, 2, 3, because this is just internal notation of the list, and this is the list written in human readable form that will result. However, this SWI PROLOG version 7 and 8 are no longer supporting this. So don't use it in this way. It is not a big deal, just simply don't use it. So I have here a few more examples here. I left them because you can find them in various literature, but don't use dot in SWI PROLOG anymore. And this will happen also in other languages in Scheme. Wherever you have language that is in development, that is alive, that is not language that was frozen in the past, but that has new and new features. From year to year, you see that something new happens, and you have to adapt to that. There is no other way. So this happens with PROLOG as well. Now, today, we have to focus on a very important topic, which is, of course, tail recursion. So whenever we process something with computers, very frequently, we have to process collection of objects. They have plenty of objects, and all of them have to be processed in the same way to do something with them. So how to do that? You either have iteration, loop that is going through that, or you use recursion. Now, in PROLOG, we use tail recursion because the vertical line is an operator that decomposes list into head and tail. And now when you decompose list into head and tail, you get tail that is shorter than the original list. You simply chop the head and then have the tail. Okay. So now, what happens when we separate head and tail? Then we can process head separately and take the tail and call the same program to process the tail. And that's the idea of tail recursion. So in each such recursive call, tail is going to be made shorter for one position. And at the very end, by doing that, the tail will be an empty list. And this empty list is the boundary condition. Or you can have that you remained with a single element, and this single element is the boundary condition. So boundary conditions for list processing can be an empty list, or the list that has only a single element, or something that has multiple elements, so you have X and the rest of them, or the list that has two elements, X and Y, or two elements plus something else. Okay, so these are all typical cases. Most frequently, by far the most frequently, you have empty list. That is the boundary condition. Sometimes we are satisfied with a list that has a single component inside or two components. So this is in 90% of cases, this is in 9% of cases, and this is 1% of cases, something like that. So this is the most frequent case. So here is an example. We want to write the program that is checking whether all elements in a list are the same. So if you have the list that has inside 1, 1, 1, 1, 1, 1, and you want to check whether all of them are the same, how to do that? Well, you can say that the list that has a single element, all of them are the same. Because if you have only one element, it is one element, therefore all of them are the same. If you have more than one, then all of them, in the case of first element X, second element Y, and the rest of them, all of them are the same. If X is equal to Y, first two must be the same. So X is equal to Y. And this is pattern matching equality. And then you have that all same are in the tail, and tail is from Y and rest. So Y and rest is the tail, and then all the same are in the tail. So these are two rules. All the same are if first two elements are the same, and in the tail, starting with the second element to the end, all of them are the same. And by doing that, you are going to eventually rest that is shorter and shorter will have only one element. So this tail will have only one element, and this is then the happy end of this program. Exactly the same thing is when you try to compute the sum of a list. So if the list is empty, the sum is 0. This is boundary condition. If the sum the list is not empty, then it has head and tail. Head is X, tail is this rest. And the sum of this element will be that if you compute the sum of rest, sum of tail, this SR, then sum is going to be X plus SR. So the sum of all elements in the list is the first element of the list plus the sum of the tail. And this is typical tail recursion. Now we have plenty of examples of tail recursion, and I'm going to go through them one by one. So the first thing is to compute the list length. First of all, PROLOG has the library function length. And if you have list L, you can have length as the result that comes from that list. So we have that this library function is most likely based not on counting how many components you have, but or comparing pointer to the first and pointer to the last element, because this is most likely stored in memory as an object, and you have plenty of pointers, and you can do that fast. But if we want to make homemade tail recursive list length function, so we can say that the length of the list is the length of the tail plus 1 for head. So the length of the list, the length of the non-empty list is the length of its tail plus 1. So what is the length of an empty list? 0. So you can say that length, which is now len, not length as the name of PROLOG library function, length of an empty list is 0. And length of non-empty list, which has anonymous head and tail, is n if length of the tail is n1, and then n, which is result, will be 1 plus n1. So the length of non-empty list is the length of tail plus 1. And this can always be written in the form of verbal interpretation. The length of an empty list is 0. The length of a non-empty list is the length of its tail plus 1. And if we can create thinking in tail recursive way, these two rules, then it is trivial to write this program. And this program will give you the length. For example, you can say, I have a list that has here 1, 2, and then you can put here 3, or you can put here anonymous value, or you can put whatever you want. What is the length of that? Length is 3. You can have even 3 anonymous values, first, second, and third. And these are 3 variables. You don't care what is the value of each of them, but the length is still going to be computed as 3. So this is working correctly. Now, for the first time, we have the possibility to write ask impossible questions, questions that don't have the answer. So this question here is, give me the list that has the length 3. So you say, there is a list that has length 3. Give me this list. Well, this list has an infinite number of objects inside. Okay, because what can be first element, second, and third can be, of course, something that is numeric value or any other atom. Therefore, what is going to be obtained as a result is that list is this list of 3 pointers, 318, 321, 324. So PROLOG is saying, if I had such list, it would be somewhere in memory, and here will be pointers to these 3 components, regardless what is their complexity. And then you can say, give me more, and there is no more, and then you enter infinite loop, and you have to abort that by putting control C. Okay, so don't ask these questions, because question that doesn't have answer is impossible in all language and languages, including PROLOG, of course. Now, another example of tail recursion, how to file list maximum. Well, the maximum of the list is obtained in, again, following 2 rules. If the list has a single element, like in this here case, so you have that list has a single element, X. This is the maximum value. So the maximum value of the list that has single element is that element. If the list has more than 1 element, then we are going to fail first rule and drop to the second rule. And the second rule tells you that the maximum of the list that has head and tail will be the winner between head and the maximum of the tail. Therefore, we are going to write rules based that the maximum of the list with 1 element is that element, and the maximum in the case of 2 or more element is the winner between head and the maximum of the tail. So here we go. PROLOG has the library function max of only 2 elements. We want to find max of a list that has an arbitrary number of elements. PROLOG does not offer such a function. It offers maximum of 2 elements. So if you have head and T max, it is going to give you maximum of these 2 numbers, but nothing more. So if we have multiple elements, we say maximum of list that has head and tail is max if maximum of the tail is T max. So take this tail, compute here maximum of the tail. And once you have T max, compare head with this T max. So maximum between head and maximum of the tail is the winner that has to be stored in the location max. This is the result that comes out of here. So if you say, give me max list of 1, 2, 3, 2, 1, max is going to be maximum between 1 and the maximum of the tail, 2, 3, 2, 1, has maximum 3. So it is maximum between 1 and 3, and this is 3 that comes as the result. And if you ask, are there more than one maximum? No, there is only one. So the maximum of a single element list is that element. Maximum of the list that has more than one element is max. If we first compute the maximum of the tail, and this is T max, and then max is going to be, the result is going to be maximum between head and this maximum of the tail. Whenever you want to compute max list, you start with the first component. And of course, if this is not a single element list, you are not going to satisfy this here, but you're going to drop down to the second one. Ricardo, what is the question?
Is there any difference between using equals and is for the assignment of max?
If you put here equals, you are going to have all this anatomy of going through the whole process. You just need to have the last value, because otherwise you will get all intermediate maximums. You know, at the end, you are going to have the maximum between 2 and 1, and this maximum is going to be 2, and this is going to be returned here, and then you go back recursively. So you can instrument this with writes, and you will see how it's going 1, 2, 3, 4 from the beginning to the end. So it is calling a maximum between 1 and maximum of tail. And this is going to go all the way up to the last element. The last thing is going to be, give me the maximum of list that has a single element 1. And then it is going to be going back. So if you put not is, but equality, you should have all intermediate results. And intermediate results are maximum of 1 is 1. Maximum of 1, 2 is 2. Maximum of 2, 3 is 3. Maximum of 2, 3 is 3. Maximum of 1, 3 is 3. And then comes 3 as the result. And you don't want to see all these intermediate results. You want to see just the last one. Okay?
Oh, okay. Thank you. Yeah, that actually would be pretty good for debugging.
Yes, that is true. For debugging, you have two possibilities. One is to put pattern matching, in which case you see the anatomy of that. But even better than that is to put print. So you can simply say maximum, I entered this function with T and T max. You can here display T and T max. And then you see exactly how is working, going step by step down. But of course, sooner or later, you execute this in your mind, and then you don't need to have these intermediate results. But yes, you can use it. We use that also for debugging sometimes. That is true. How to show list elements. So I have list A, B, C, D, E, and I want to show all these elements. Okay, how to do that? Well, to do that, we have to create the show list program. How to show all elements. We already did that a minute ago. So you show the head of the list and then call the program that shows the tail. So to show all elements in the list, you first display head and then call the same program to display the tail. So show list that is empty list is going to be just new line. You have nothing to do and put new line for showing an empty list. If the list is not empty, we fail this rule number 1 and drop to this rule number 2. And we have show list something that has head and tail. So this vertical line is decomposing head and tail when you match this with the list. So head and tail is going to be matched with A, B, C, D, E, because this A, B, C, D, E is not matching empty list. So you fail here. You drop down and then take list A, B, C, D, E and match head and tail. This is going to create head is A and tail is B, C, D, E. Okay, so Now, since we have this head that is separated from the tail, we are going to display the head. And head is going to be this A, and we are going to display this A. After that, displaying A, we are going to put one space, tab 1. So this is this space here between A and B, this space here. And then we have show list of the tail. And tail is B, C, D, E. So go here and take this list, B, C, D, E, and compare it with this empty list. It fails because it is not empty. Drop down, and you have B, C, D, E as the list. So head of that is now going to be second element B. Tail of that is going to be C, D, E. You go here, display head. Head is this B. Put one space. This is this space between B and C. And then show the tail, which is C, D, E. And so continue in that way. Show first, show second, show third. So always chop head, process head, and apply the same procedure to the tail of the list. Sooner or later, you're going to reach an empty list. And this is going to be the end of the whole story. Okay? Tail recursion. So this is tail recursive program. Chop head, process tail. Chop head, process tail. Always the same. There is a gazillion of problems that can be solved in this way. And this is very powerful technique. And it is, of course, applied sometimes in procedural languages, C, C++, Java. You can do that, of course, but you are not chopping the tail, you are chopping the last element of an array. So if you want to display the array, you say display the last element of array, which is array of index n minus 1. So this is the last element, display that. And then call the same program to display the same array, but not with size n, but with size n minus 1. And then it is going to display last element before last, and finally the 0 element, and then we'll go out. Okay, so this is the way how this is recursively done. So how to test if an object is a list? Well, we can do that in this way. An object is a list if it is terminated by the empty list. So you can go through all these components, first, second, third, up to this last component. You cannot say, is this the list or not, unless you reach the end of this list. So this here is not a list. It is a tree because it doesn't have here the terminator, which is an empty list. So if I want to see whether this is the list, I'm going to say that this is the list if the tail of this list is a list. So you are always saying a list has the property, the tree has the property of the list if the tail of that tree is a list. And this is what you have to do. And you go from the beginning to the end in this way. So here is the program. An empty list is a list. That's the first rule. The second, a non-empty list is a list if its tail is the list, in that case. Okay? Non-empty list is a list if its tail is a list. So an empty list is a list. You say is list, empty list, this is going to match, and answer will be yes. And then non-empty list has head and tail. Head, if you put here head, H or whatever else, PROLOG will instantiate that and will start complaining. Will say, why you are instantiating variable that you are never using? And this is legitimate question. So you put here anonymous element, and then you have the tail that you are using. So an empty list is a list, and non-empty list is a list if the tail is the list. If is list the tail. So is list an empty list, or is list non-empty list if it has an anonymous head and tail, which is a list. And that's all you have to do. And this is remarkably short, and there are no indices, and you simply go through the whole list till the end and check whether is the list or not. This is homemade is list, and library function has the name is_list. Yeah, is the library function, and this is homemade function that is doing the same thing. You can check whether something is a tree, and it is tree if you have head and something that you can chop after that. So it is a tree structure. What is at the end? Nobody knows. It can be terminated with empty list, in which case it is a list. Otherwise, it is a tree, which is not a list. So these things are possible, both of them. Then last element of the list, how to write the program that is going to find the last element of the list. The last element of the list is found using the same recursive reasoning. So if the list contains one element, this is the last element. So if you have only a single element, this is the last element. If the list contains more than one element, then the last element is the last element in the tail of the list. So this is the way how to find the last element in the list. You have plenty of elements and you want to find the last one. So last element in the list that has a single element is that single element. If we fail this first rule, then the list has multiple elements, head and tail. So last element in the list that has multiple elements is list. If last element in the tail is that X. Okay, so last element in the multi-element list is X if it is the last element in the tail. And so this is going to chop these anonymous heads, first head, second head, third head, fourth head, up to the last element. And when you have last element, single element, then the first rule will work. Pay attention that you cannot reach this second rule unless you fail the first one. So the first one says that list with a single element is this element as the last element. Nice. But you have to have here single element. As long as list has more than one element, you are failing this first rule and dropping down. So it is practically calling last element, last element. So it is doing first, second, first, second, first, second, as long, and in each iteration, chop, 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 chop the head. And at the end, will come with single element in the tail, and will come here with single element and this X, and then it is going to return that X, and this is the end of story. So you have this result, and this result is going to be given to you. So any question about this? Okay, now one thing that you have to understand, when you see these things the first time, this looks a little bit strange. And before you start thinking recursively in this way, you are going to have some effort to understand that. And therefore, read all these things and play with that at home to see how it works. So look at this last element. I have here last element of A, B, C, D, E is X. What is X? X is E. That is the last element. I can say I have, and this is flexible, by the way. There is no assignment inside. So you can say, I have the list A, B, C, D, X that has the last element E. Tell me what is E, what is X? And of course, X must be E. So you can ask, what is the last element here? Or you can have lists that consist of more complex objects, A, B, C, D, and here is 1, 2, 3, and 4. And we ask, what is the last element? Well, this is 1, 2, 3, and 4. So it is giving you last object in the list. Now, the question, you have a list, and I want to have two adjacent elements in the list. What are two adjacent elements in the list 1, 2, 3, 4? 1, 2 are adjacent, two of them. 2, 3 are adjacent. 3, 4 are adjacent. So adjacents are X and Y in this list. And give me X and give me Y. So PROLOG will say X is 1, Y is 2. Excellent. And I enter semicolon and say, give me more. Then PROLOG say, you have 2 and 3 that are adjacent. I say, beautiful, give me more. PROLOG says, give me 3 and 4 are adjacent, 3 and 4. I ask, give me more than that. The answer is no. There is nothing more. 1, 2, 2, 3, and 3, 4 are adjacent. No more than that. How to write the program? Two first elements in the list are adjacent elements. Do you agree with that? First two elements are adjacent. If the list has multiple elements, then if the adjacent elements are not the first two elements, but something else, then they may be two adjacent elements in the tail of the list. So they are either first two elements or two adjacent in the tail of the list. Here we go. Adjacent in the list XY with anonymous tail are X and Y. First two are adjacent. No problem with that. Adjacent are XY in the list that has anonymous has and tail if X and Y are adjacent in the tail. Okay. Now, one thing that you see here is that I have here three variables, X, Y, and this third one. Any permutation of this X, Y, and the third one will work the same. So you can say I have the list X, Y, anonymous tail, and what are two adjacent elements, X and Y. And then I can put this here as the first. Here we say adjacents are X and Y if you have the list where you chop the head and you have the tail and they are adjacent in the tail. And then this adjacent called this adjacent and so on and so forth until all results are obtained. This is a flexible predicate. Rules are rather simple, and therefore I can say this. I have the list 1, 2, 3, 4. Who is adjacent to 2? So 2 and Y are adjacent in this list. What is Y? So you go here and matches 2 matches this 2, Y matches this 3, therefore Y is 3. I ask who else is adjacent to 2? Nobody else. 1, 2, 3, 4, it doesn't have other component that would be adjacent. So you can ask also this. Give me two adjacent elements in the list 1, 2, 3, and 4. So this list has 3 elements. Adjacents are 1 and 2, 3, and adjacents are 2, 3, and 4, and nothing more. Okay? Any question about this? Whenever you want to ask the question, just unmute your microphone and ask. That's the simplest way to do things. Or if you just want to be extremely polite, raise your hand, but just start talking and no problem with that. Now, member of a list, we want to check whether a component is member of the list. This is extremely frequent problem. It is an extremely frequent problem to find member of the list because member is necessary to check collection of objects and to see what is inside, and therefore you have to test member with all components of the list. How to do that? Well, we have that member of the list is the head of list. So you can say the head of list is the member of the list. If the member is not the head, it is maybe somewhere in the tail. So it is either a head of list or it is somewhere stored in the tail of the list. So what we have here as the first rule is that for the list that has anonymous, that has head X and anonymous tail, X is member of that list. So X is member of the list if X is head of list, and I don't care what is the tail. Okay. Now, this is called member one because member is a library function, and therefore I don't want to have compromise to have the same name, because that would be redefining library function. You don't do such things. So member one is the name of it. So we have that X is a member of the list where X is the head. If X is not the head, what then? Well, then member of the list is the member of the tail. And the head is whatever you want, something that is different from X. But are you sure that this is different from X? Can somebody answer? Can this anonymous value be equal to X?
No, otherwise it would have been the first condition.
Bravo. You cannot come down here unless you fail the first rule. Excellent. Why? Because if this X is equal to this head of list, you would succeed already here and will say, yes, it is the member, and will stop the program. So once that you arrive to second line, that means you failed the first one. Therefore, X and this head of list are different. So you say, now I know that this is different from X. So I'm looking whether X is somewhere inside the tail. So it is the member if it is member in the tail. And that's all what you have to do. So these are two lines that solve this problem. And this is elegant and readable and understandable. And you can play with that. So you ask whether 2 is the member of the list 1, 2, 3. The answer is yes. Is 7 member of 1, 2, 3? The answer is no. So what is X if X is member of 1, 2, 3? Well, X can be 1, X can be 2, X can be 3, and nothing more. Now, these semicolons are something that I entered. So when I say member is X is 1, 2, 3, the result will be X is 1. And then PROLOG waits here to see what I want more. I say, give me more. Okay, X is 2, and then it stops here. And then I say, give me more. X is 3, comes after 3. Give me more. No, there are only 3 of them. Okay. Now, you can say 2 is the member of the list 1x3. What is X? Well, X is 2. Simply because 2 cannot match 1. 2 can match this X. So X is 2. And 2 cannot match 3. Therefore, there is nothing more. There is only X is 2. And when you ask, what is the list 1x3, so that 2 is the member of that list, X is 2. I can use also impossible question. I say, give me the list where 2 is a member. Ha! How many lists do we have where 2 is the member? Of course, an infinite number of lists. It is not 1, 2, 3, but it can have any number of lists. So what is going to be the reply that you get from PROLOG? It is telling this list is the list that has head 2. And the tail is an object that would have pointer in this location G3.14. Okay, so this is the place where the pointer is set for object that comes after that, which can be a list that has a million components. Then you say, bravo, I'm very happy with that. Give me more. Then PROLOG says, you know, the second would be something that has head that is pointed by this pointer, then has 2 as the second component, and then the third component would be in 317. Beautiful, give me more. 313, 316, 2, and then 320. So this is the case where 2 is the element number 3 in this list. That has here first element, second element, 2, and here gazillion of elements. This is, of course, completely useless. But it tells you that PROLOG has, with this program, a proper way of reasoning. It is creating objects of higher and higher complexity, putting 2 inside. Of course, don't do these things because these are unsolvable problems. But if you say, is 2 member of the list that has only one element? Yes, it is. The answer is yes. Now, you can have the library function member, and the library function member is member without one. So member is the library function, and you can ask, give me member of the list 1, 2, 3. So the first answer will be X is 1. Then I put semicolon and say, give me more results. Well, X is 2. That's the second answer. And the third answer is X is 3. I say, give me more, false, no more answers. So either you get false or you get no. But this is the fact that there are no more solutions. So solutions are 1 and 2 and 3 for X to be member of 1, 2, 3. Now, you can also write this question or this rule by putting cut after that. So what is going to happen if I write, give me member X that belongs to 1, 2, 3, and after that, create this cut. So what happens now? Now, PROLOG is going and matching this X with 1. First that, with the head of the list. And X is at this moment 1. But this is not the result, because I have here that member has to satisfy also this cut. And then cut is satisfied, search engine jumps here, comes to this position, okay? And then at this position, it becomes clear that there is no way back and there is no way forward. Forward is the end of this rule and left is cut. So PROLOG knows that the result that is obtained is one and only result. And therefore will print X equals 1, will put dot and will put prompt and will say, what do you want now? So it is not going to give me possibility of choice, okay? Because in this case, when I have member of, member is X is 1, 2, 3, where is now the pointer? The pointer is here after this parenthesis and before this dot, that's where the pointer of the search mechanism is. When I say, give me more, what is going to happen? PROLOG will try to go right. There is nothing right. It says, I must backtrack. And will backtrack back to this one and only line that you have, and will go from the position after 1 was processed, and will bring me 2, and will stop here between 2 and 3, and will wait. And again, if I say, give me more, it must go right. There is nothing right. Therefore, it must go left. It must backtrack and will backtrack to 3. But here, we prevent backtracking. We are going to put the pointer here at the end, but you cannot go back. So you create only the first solution, and after the first solution, you terminate the program. There is nothing more. So this shows the role of cut in the case of this very simple problem. Now, we have one little more complex problem. We want to write the function that is appending lists. Append list L1 plus L2 to get list L3. So how to append 2 lists, to glue them together? Okay, we want to write program for that. There is library function append, so I'm going to write the program append 1 to make different from append that is library function. Now the idea is this: we have this list L1 that is painted blue here, and list L2 that is painted yellow. We want to merge together these two lists to get the third list. When you match blue and yellow, you get the green one, of course. So what you have, A, B, C, D, that are components of the first list, and after that you have 1, 2, 3. So how to append these two components? Well, if you go from left to right, then you can say that appending this list 1 and list 2 will create the list 3 that has the same head as list 1. So this A has to be copied from list 1 to list 3. And the tail of this list 3, which is denoted as T3, will be obtained as tail of T1 appended with 1, 2, 3, with list 2. So going back to this explanation is that to append list 1 and list 2, we are going to copy the head from list 1 to list 3, and we'll create the tail of list 3 by appending tail of list 1 and list 2. This is the tail T3. And now this helps you to understand the reasoning that we apply here. So since we are going to move head and then next head and next head, sooner or later, this T1 or L1 is going to be empty list. So when you append empty list to list L2, we are going to get L2. That's the boundary condition. If we have something that has head and tail to append to L2, we are going to get the list L3 that has the same head. So this head here propagates to the head of the resulting list. And this is copying this A to A. Head, head. If I can create T3, which is tail here, by appending tail T1 and list 2. Tail T1 and list 2. And that is creating tail 3. So if I have this kind of append function, this is something that can work in a very flexible way. And this is extremely important slide because it shows interchangeability of inputs and outputs. When you have this append program that I have here, you can ask, if I append 1, 2, and 3, 4, what is the result? Is the result 1, 2, 3, 4? All of them are inputs. PROLOG says yes. I say, I have to append something to 3, 4 to get 1, 2, 3, 4. What is this something? It is 1, 2. Anything else? No, only that. I want to append 1, 2, and y to get 1, 2, 3, 4. What is y? Y is 3, 4. Anything else? No. I want to append two things, x and y. Give me x and y so that when I append them, I get 1, 2, 3, 4. What you can do is to have the first result, append empty list and 1, 2, 3, 4. This is going to give you 1, 2, 3, 4. We ask, give me more. Append 1 with 2, 3, 4, or 1, 2, and 3, 4, 1, 2, 3, and 4, or 1, 2, 3, 4, and empty list. Anything more? No. So there are 5 solutions here, 5 solutions that are creating these results that we have here. So 1, 2, 3, 4, 5 pairs. And all of them you get. Now you can also play more complex games and you can say, I want to append 1, 2, and 3, 4. What is the appended list? 1, 2, 3, 4. You can say append 1, 2, and 3, 4 to get 1, 2, x, 4. What is x? 3. Append 1, y, and 3, 4 to get 1, 2, x, 4. What is x? What is y? Y matches 2. X matches 3. And 4 matches 4. Okay? So you're going to get that and 1 matches 1, that is correct. So y is 2, x is 3. Here, 1y, append with 3z to get 1, 2, x, 4. What is x, what is y, what is z? Well, 1 matches 1. Y matches 2. Y is 2. Then 3 matches x. X is 3. And z matches 4. Z is 4. So it is 2, 3, 4. Perhaps give me more? No. I can also say x2 and 3, 4 should produce y2, 3, 4. Obviously, x should match y, but they are uninstantiated variables. So PROLOG tells they would have pointers in G365, both of them, but nothing more than that. Okay, any question about this?